All right, so chapter 2 is all about one-dimensional motion. Chapter 3, unit 3, talks about projectile motion. So instead of one direction, either up or down, we actually have two directions, okay? And we could be moving in two directions at the same time. If we have a projectile, we're moving in the x and we're moving in the y, all right? So I wrote this before. In the x direction, it's positive this way, negative this way, positive y, negative y. And that's going to be important for us, all right? So our original equations are VF equals VI plus AT, VF squared equals VI squared plus 2AX, and X equals VIT plus 1/2 AT squared. So I want you to think about a projectile, all right? Let's say we're on a cliff and we're launching it directly out. It's going to fall to the ground, okay? Now the only thing pulling on this is gravity down. A little bit bigger and then bigger, all right? And so this would be like the velocity. Is that the velocity in the x direction? No, it's not. It's the velocity in the y direction. So we could put velocity in the y. Now if we think about the x direction is not being affected at all by anything. We assume that there's no air and a bunch of other things. That x velocity is always going to remain the same. And I think that makes sense. Like if you roll a ball and there's no air or anything or friction, that ball's going to roll the same speed forever. That's our x direction. Now if I toss a ball or I drop a ball from a sky, my velocity in the y direction is going to increase until it hits the ground. All right? So here's the deal. In the x direction, there is 0 acceleration. In the y direction, the value is gravity. So how does that affect our equations? Okay? We're going to have one set for the x direction, and we're going to have one set for the y direction. Okay? The fact is when we do these, they have to work independently. We have to look at the x, we have to look at the y, we cannot look at them together. Okay? It just doesn't work that way. The reason is because you would have a constant angle changing. We'd have to keep calculating different angles and make it hard, and make it impossible. All right, so how does this affect things? Well, let's just look at the x direction. Okay? If we just look at the x direction, and I say that the acceleration is 0, what does that do to our equations? Well, this is 0, this is 0, and this is 0. VF equals VI, that makes sense, it never changed. VF equals VI squared, that's right, never changed. And then down here, all we have for the x direction is x equals VIXT. Okay? Now you notice I added a little x here to designate it as the x direction. Right? Because if we're going to keep them separate, we don't want to confuse the x and y direction. It's weird writing it from the middle. All right, so we took care of this, the x. Now how about the y direction? Okay, so everywhere that we see A, we're going to put G. Okay, and how about everywhere we see X? We could put Y. All right, so let's rewrite those for our Y direction. So we're going to have VFY, make sure you write that it's the y direction, equals VIY plus GT. Time's going to be the same for both. VFY squared equals VIY squared plus 2GY. And then y is equal to VIYT plus 1/2 GT squared. Okay. So we put these little extra, for our subscripts, we put our little extra y's and x's in just to make sure we remember when we do the problem that it is the y direction or it is the x direction. The only thing that you can see that goes in both is time. Okay? So we can actually solve for time over here and put it in here and vice versa. All right, when we do these problems. That's the only thing that's unique. We cannot do anything else. Now, why is that? Okay? So let's say we have what I call a ground-to-ground problem. So a person is throwing a ball and it's landing on the ground somewhere else, or you have a cannonball being shot and it lands on the ground. It's going to look like this. All right? Should be symmetrical, should be perfectly symmetrical because there's no air. If there was air involved, we kind of have this launch. If you've ever seen a golf ball hit from the side, it kind of goes up and it kind of stalls out and falls. All right, but ours is going to be hopefully perfectly symmetrical. All right, so at the beginning, we have an initial velocity at some angle. Now that initial velocity can be separated into two different vectors. One, that didn't help, did it? One in the x direction and one in the y direction. Ah, who cares? Good enough. So this would be our VIY. This would be our VIX. Okay? So the first thing we're going to do when we do these problems, we're going to split the initial velocity into two separate vectors. Okay? And see, now we have our VIX and we have our VIY. So why is the time the same? So if we think about a ball being tossed right here, okay, and it goes up and it comes back down and it's launched with VIY. So I always think of this in my head. I have a ball, I'm tossing it, and I have another one that I'm rolling. So it'd go like this. So halfway, when this object is halfway, a ball rolling with this velocity will be here, and the ball, if it was tossed straight up, would be at top. And then they would come back down, this would come back down, and this one would be at the end. So it's kind of a... So the time it takes the object to go up and down is the same amount of time it takes to go all the way across. All right? That's the only way that we could have time being on both sides because they are the same. All right? Now there's three types of launches that we could have. One is off a cliff, or two are off a cliff, and the other one's on the ground. All right, so there's three types of launches. One is a horizontal launch off a cliff, where the initial velocity is some number, and the initial velocity in the y direction would be 0. All right. That could be a person throwing a baseball like this, horizontal. It could be somebody kicking something or rolling a ball off a table or anything like that. I call that horizontal launch. Then we have ground to ground. Right? Where we do have to take our vector VI and we have to separate it into VIY and VIX, which we'll use trig functions that you would see in another video. And then we have a cliff. These are the hardest ones, where we have an initial launch. Once again, we have to find VIY, VIX, but it's actually going to launch up off a cliff, so I don't know what I call that. Cliff at an angle, something like that. These are the most difficult, okay? But those are our three types of launches, and our example problems that we're going to have in our homework sheets are going to focus on these three types. So when it comes to projectile motion, you got to follow some steps, okay? And these are all going to be given to you, or you're going to see them in notes. One, you have to find the components of the initial vector, okay? The initial velocity. We have to find the components that are made up of them. And when we do that, we have to stop thinking about our launches as being curves. we have to think like two separate things that are connected by time. One, throwing a ball up and catching it, okay, or dropping it. In this case, it'd be dropping it. That would be our vertical, and then our horizontal. This one, throwing a ball up, coming down, and then a ball rolling this way. And then this one, throwing a ball up off a cliff, and then the other one would just be it just moving this way at a constant velocity in x direction. So we have to separate them by using trig functions, okay? And we have to start just saying, okay, we're going to look at these two things differently. Rolling a ball, one equation, up and down or dropping it, we have 3 equations for that. Secondly, you always have to find time. There's not a single situation that you don't need time, right? Time could be given to you, which is absolutely fantastic, but you have to find it. And I'm going to say this. The vast, vast majority of the time, you're going to have to use the y direction, okay? You have 3 equations, right? 2 of them have time in it. X direction, only 1, all right? A lot of times, the questions will ask you, what is the range? And when it says, what is the range, what they're asking is, like, what is this? What is x? So if they're asking for that, there's no way, because we only have 1 equation, that we're going to be able to solve for time with it, all right? So focus on the y direction to find time. Thirdly, find everything else. So I have 3 rules. Find the components of the vector, find time, find everything else, whatever they're asking for, all right? And there's videos that will also show the example problems and whatnot.